Welcome everyone to the third day of this discussion meeting. So we will start with Professor John Loftin. So he will again continue minimal surfaces, equivalent minimal surfaces in complex hyperbolic space. So,
Okay. Hi. So thanks for the introduction, and thanks for everyone who knows when 9:30 is. So because it's an earlier time. So I'm going to kind of actually talk about a different symmetric space, not complex hyperbolic space today. So kind of the title of this talk would be kind of cubic differentials and harmonic maps into a, it's going to be minimal surfaces, harmonic maps into a real building. So I'll explain to some extent what these are. And this is joint with Andrea Tamborelli and Mike Wolf. Good. All right. So the start of this is some work of Hitchin. So Hitchin, to some extent, kind of started this new-ish field of higher Teichmüller theory by expanding his parametrization of Teichmüller space, which we discussed yesterday, to parametrizations of a certain component of representations into other split real Lie groups, whereas in Teichmüller space, you would look at kind of PSL2R. That's kind of, so it turns out that there's a version of this. So the group here is going to be SL3R, maybe PSL3R, Higgs bundles. So for us, we're going to have over sigma. So again, this is going to be a Riemann surface, which is compact and genus at least 2. So it has a background hyperbolic metric if we need it. And we're going to have a vector bundle. So in this case, the vector bundle is going to look fairly similar to before. It's going to be the canonical bundle plus the trivial line bundle plus the inverse of the canonical bundle. So you recall recall from the kind of the SL2R case, we had a rank 2 bundle, which involved kind of taking a square root of the canonical bundle, k to the 1/2, and then k to the -1/2. So you can kind of see that there's kind of a little bit of a pattern here, and because 3 is odd, you don't have to take the square roots of the bundle. And Hitchin does this for all of the SLNR, and kind of using some work of Costant on the principal three-dimensional subgroup, I think it's called principal, then he can extend this to all split real Lie groups. Okay. All right. So this is the bundle, and so what we're going to have is a Higgs field. So again, we're going to have the Higgs field is going to live in the canonical bundle tensor endomorphisms of E. And since E is a product of kind of these powers of the canonical bundle, again, we're going to have kind of we're able to write this down by as a matrix, kind of considering this as kind of a basis of E. Okay. And so in this case, we will choose, so this is Hitchin's choice. So this is Hitchin in 1992. We're going to choose Hitchin. So let's see. Phi is I screwed that up. Let's see. So 1, 1, 0, 0, okay? Where Q is going to be a quadratic differential, and U is going to be a cubic differential. Okay? And again, so this diagonal here, this would be abelian differentials, just sections of K itself. We're choosing that to be 0. This would be sections of K inverse. That's going to be 0 as well. I mean, and this is going to be sections of the trivial bundle. So we can just choose the constant 1. There's a canonical identification. Okay? All right. So given this, Hitchin kind of parameterizes a component of the representation variety. So let's say so I think we probably need a P here. Or actually, I keep forgetting, but a P is safe enough. And then you divide this out by conjugation. Okay? Via all Q and U for a fixed sigma. Okay? So if you have a base point, kind of a Riemann surface in Teichmüller space, so this is going to be in the Teichmüller space of S, so S is going to be just the topological surface behind the Riemann surface, the conformal structure. So then if you fix sigma, then you vary Q and U, you get all of this component via this Higgs bundle construction. And so this is, okay. And of course, these representations come from this flat connection, which we'll write down later. But it turns out, so in this case, so this is due to kind of various works of myself and Labrie and Choi Goldman, and then kind of superseded for all kind of rank 2 split real Lie groups by Labrie's work, is we can replace, we can allow Q equals 0 by letting sigma move in the Teichmüller space. Okay? So in particular, this is going to be a bundle. And so the bundle is going to be, so this is going to be a vector bundle over Teichmüller space, and the fibers here are going to be the space of cubic differentials. So over a given Riemann surface, this is the space of cubic differentials. So this is a vector bundle over a Teichmüller space, okay? And so this is actually kind of a nicer description, because when you write it this way, then this is invariant under the mapping class group. Oh, T of S, Teichmüller space. Okay, yeah, so I should, yeah, I guess I would say, yeah, so this is Teichmüller space. Yep, thanks, yeah. Please do keep me on my toes with that sort of stuff. So, yeah, I'm trying to make this like not a J, but like a little funny T, so. Okay, okay, so I don't know how to do that, so, all right. Okay, and so and as we'll see with kind of Nathaniel's work later, this description works by Labrie's theorem for all kind of split real forms of all rank 2 split real Lie groups, which, I mean, there's SL3R, I mean, a semi-simple split real Lie groups. There's a kind of just a product SL2 cross SL2. There's SL3R, there's SP4R, and there's split G2. For all the other cases, this does not work. And that's kind of, I imagine, or it's possible that Nathaniel will talk to us about that soon enough. Okay. All right. So then, given this, so in this case, what we have is we're going to have a, So let me just kind of go ahead. So this is going to be the Q equals 0 case, which we can do. Then we're going to get a harmonic metric so on E given by the following of the form, which is also diagonal, as we saw in kind of Hitchin's situation last time. And this uses the fact that Q is equal to 0. In general, you're going to get kind of a metric which is not diagonal if you have kind of this more complicated thing. But we're allowed to restrict to this in the rank 2 case. And so this is called, and so H, this is going to be a metric on, so little h is a metric on K inverse, and you can just think about that as a metric on the Riemann surface. So this is going to be a conformal metric on sigma given by, I guess, called the Blaschke metric. Okay. So this kind of relates to kind of some work of Blaschke over 100 years ago in affine differential geometry, which I may or may not have time to talk about that. We'll see how much time there is. Okay, and then we're going to have nabla. This is going to be, again, the connection. So this is going to be M. So the Chern connection of M plus phi plus the dual with respect to this, this metric M. This is flat. You can check that the degree of E is 0. And so, and again, kind of the harmonicity is that this is a harmonic. And indeed, it's kind of minimal. Oops. When Q is equal to 0. So when Q is equal to 0, you can use the same formula, kind of the trace of phi squared, and notice that that is the Hopf differential that vanishes when Q is equal to 0. Okay? So this is kind of a way of constructing these equivariant minimal surfaces. So you construct kind of both the representation, rho, and so I guess I should say, so the holonomy of nabla gives the representation rho of pi 1 of sigma into SL3R. Okay? And again, so this is going to be these are kind of naturally complex vector bundles, so it would be like SL3C, but there is a real form, which is not quite the standard one where you can put this into SL3R. Good? All right. Okay, so I'm going to say, I'm going to give this space, the symmetric space, the space of these metrics, a name. I'll just call that X. And for this symmetric space, this is a symmetric space of non-compact type of rank 2. And so the rank of the symmetric space is going to be the largest copy of, so for rank 2, that means that there's a copy of R2 which is isometrically embedded and totally geodesic inside the symmetric space. So, and so it's not, and so there's no R3, that would be rank 3, for example. This is different from, say, kind of the hyperbolic plane, CH2 And H2 that we talked about before, those are both rank 1. So they're kind of copies. So they're isometrically embedded, totally geodesic copies of R2 in X. Okay, and so these are actually going to be useful for us later. So let me just kind of write down. So these are called flats. These kind of copies of R2, and there's a standard one. So we can kind of represent. So I guess I should say represent X again as a space of metrics. So not necessarily as this quotient, but it's useful to kind of think of it as a space of metrics. As these are going to be positive definite metrics on R3 with volume 1, so determinant 1. That's the the S condition. So otherwise you just get GL. Okay? So then there's a standard flat is diagonal, is given by diagonal matrices, and so these have to be positive, so it's going to be something like this. And so if you think about this, instead of just in the symmetric space, but in the larger Lie group, then you can see that this is kind of one of the standard maximal tori in SL3. Okay? So I'll call this kind of a maximal torus. And so I think maybe you usually take a dual, but I'll call this T. Yes. It's not Hermitian. It's 5-dimensional. It's not. Yeah. Yeah, so this one is, so it doesn't have kind of the exact same structure, but it's, yeah, it's not Hermitian. Okay, so I'll call that maximal chorus T. And so one of the things that's going to be useful for us to understand the geometry in the building is, so how do the flats intersect? Okay. So I guess one of the things that this is going to be in, say, in the Lie algebra of SL3R, and so this is just going to be real lambda satisfying this condition. So this actually puts things in a plane, and then of course we'll have the standard kind of Weil chamber picture, which will come up. Okay, so I'll explain this a little bit in a minute. So how do different flats intersect? And it turns out they intersect in such a way that it respects kind of the properties of the affine Weil group. So kind of reflections across these lines in the Weil chamber plus translations. And then just any translations. There's no integrality condition or anything in this case. So, so how do these flats intersect? This is going to be the, so let's kind of, we could talk about another example. So another flat that's related to this one is the following. So we want kind of, and basically, this is going to be an abelian subgroup of SL3R, and it lands in the positive definite matrices. We want to find another one, and that's going to be related to this. So this is going to be the following. So where alpha and lambda are in R, are real parameters. Okay? So you can check that this is abelian, again. And you can see it's related to this one. So it's just that this one is diagonalized in the standard way. And in order to diagonalize this one, you'd have to kind of change this upper block here. Okay? And so these intersect when, in terms of this notation, lambda 1 is equal to lambda 2. So I mean, if you have these two eigenvalues being equal, then there are, so you can think of this as kind of a this little block is a multiple of the identity. And so of course, if you're looking for other matrices that commute with a diagonal matrix, it depends on whether the eigenvalues are equal or not. So if this is essentially a multiple of the identity, you can write down something like this. These will all commute when lambda 1 equals lambda 2 equals lambda here. Okay? And then, okay. So these are the way these intersect. And this is exactly kind of this is going to be lambda 1 equals lambda 2 is a wall of the standard of the Weil chamber, of this Weil chamber picture. So so in particular, the Weil chamber in T. So we'll talk about. So there's a standard positive Weil chamber. Is, for example, what's this? Lambda 1 bigger than lambda 2 is bigger than lambda 3. Then, of course, plus the sum is equal to 0, right? And so this we may call W plus. And notice that this lambda 1 equals lambda 2, this is a wall separating the Weil chambers. So each of the Weil chambers depends on the ordering of these three eigenvalues, or logs of eigenvalues. And so there are 6 of them corresponding to the symmetric group in this case. And the wall of the Weil chamber is when 2 of them are equal. So this may be the locus where lambda 1 is equal to lambda 2. And then in this one, we would have lambda 2 is bigger than lambda 1 is bigger than lambda 3, for example. So this is how these things intersect. Okay. So it's going to be useful for us to kind of write down the metric, which is given by the Killing form on X. And I'm going to write this down as a metric space metric. I'm not going to worry with kind of the Riemannian structure, which it has. So I want to compute the distance from the identity matrix to A times the identity matrix, where A is in SL3R. So this is the action of A on this quotient. And so this is, of course, if you write it this way, it's left multiplication. But if I want to write it as a metric, then it's something else going on. So, A times the identity, this means, so this is in SL3R mod SO3. This is going to be equal to A transpose times the identity times A. Okay, so this is in kind of positive definite metrics. Okay, so this is just how the group acts if you write this down like that. And so then the distance here is going to be the square root of what's known as the singular values of A. Where sigma I squared is going to be equal to log of the eigenvalues of A transpose A. And so these are going to be the okay. So these are going to be the singular, what's known as singular values. Sigma I of, I believe, of log A. Okay. Okay. So this is kind of the way you can. So this is the metric. It kind of depends on these things that look kind of like eigenvalues, but are not quite the same. And so then what we're going to do is we want to kind of take kind of our idea is to consider U, this cubic differential, which is not identically zero, and kind of replace it by t times u, where t goes to plus infinity. Okay. And so we want to analyze the geometry in this limit. Yeah, it's not, yeah, let's see. I think hopefully I got this correct. So, yeah, I'm not sure if the log goes here or the log goes here. So, yeah. So something like that. So yeah, maybe this is a little bit questionable, but this formula still works. All right. Okay. Thanks. All right. So what we want to do is we want to consider kind of the structure given by this. And so in terms of, so it turns out that kind of the Blaschke metric and the other data. So this is the, so I guess this would, I'd be calling this M. So this is the map into the symmetric space M. So these are going to scale by tau equals the cube root of t. Okay. And so the natural thing to do is to take kind of what's known as an asymptotic cone. So we're going to take the Gromov-Hausdorff limit of x with respect to tau inverse times this metric space metric on x. Okay? All right. Okay. And so this will give us kind of, since this is kind of, we're dividing out by the natural scaling, this will give us the structure that we want. Okay? So this is as t goes to infinity. Okay, and so now it turns out that in general that this space, you have to kind of do something and kind of make some strange assumptions to make sure that this space actually would converge in this asymptotic cone. And so what happens is we need kind of something called, let me double check what time it is, 9:58. So we need what's known as non-principal ultrafilter. To assure convergence. Okay? So, so basically the idea is that you know that if you have a sequence, right? So a sequence kind of that is kind of a sequence where kind of the indices are the natural numbers. You know that you can take subsequences, right? And so that's kind of the standard notion of compactness. You take limit, you take a subsequence. And then there's even this kind of amazing fact that, due to Cantor, I believe, is that if you have to take subsequences a countable number of times, you can use this diagonal argument and find a common subsequence and still get a limit. So it turns out, and I'm not really an expert on this, it turns out there are situations where having a countable number of subsequences is not enough, and you need some mechanism that will work with possibly an uncountable number of choices. And that mechanism is something called this non-principal ultrafilter, which I'll kind of describe quickly here. and that is that, so what we want is, so first of all, I'm going to let, so I'm going to do this in terms of tau. Let tau I be a sequence going to plus infinity. Because, I mean, the ultrafilter really works on the natural number, so I want to kind of reduce from the, this real limit to a sequence, first of all. And then we're going to have, so I'll have to kind of start over here again, the, so this is going to be a non-principal ultrafilter on the natural numbers. Good. So this is going to be the following. So omega is going to be a finitely additive measure on n. Let's say a probability measure. So the entire natural numbers has measure 1. It has all sets have measure 0 or 1, and all finite sets have measure 0. Okay? So it turns out that these, in order to get these to exist, you cannot write them down. You need the axiom of choice. But they do exist. And this gives us, so basically every subset of the natural numbers has measure either 0 or 1. And when you have kind of a, so imagine, and each subset, that represents something like a subsequence, right? So imagine that you have a choice, you have your subset, and you have kind of, you're either going to go, say, with the odd numbers or the even numbers. For a non-principal ultrafilter, one of those sets will have measure 1 and the other will have measure 0. You pick the one that has measure 1. And then at every time that you have a choice like this, there will always be one that has measure 1, and you throw away the rest that have measure 0. Okay? And so in that way, you pick a subsequence, and somehow this kind of alleviates the difficulties that you may have in constructing this sort of asymptotic cone. Okay? So, and then there's kind of, so if I've already kind of committed a faux pas by mentioning the axiom of choice, let me go ahead and make it worse. So, so it turns out that for X, a symmetric space, this kind of limit, you kind of write this as limit as according to the non-principal ultrafilter of, say, X tau inverse dx is independent of omega if you assume the continuum hypothesis. So this is in terms of kind of, so that means that kind of the cardinality of the real numbers is the next largest, is it ordinal or cardinal? It is the next largest cardinality after the cardinality of the natural numbers. Okay, so this is just kind of a little bit of background, but I wanted to explain a little bit about this. And what happens here is that, so you can take this limiting space, this asymptotic cone, has the structure of a real building. And this is kind of a somewhat complicated, somewhat algebraic object, but I'll just explain it. And so in other words, a few relevant properties. So this is going to be a union of apartments And so these are going to be copies of the relevant maximal torus, which is R2, which is just isometric to R2. And these are going to be glued in a way that respects the affine Weil group. So in particular, you can kind of glue two of these things together by identifying one Weil chamber together, or by kind of, if you consider the affine Weil group, you could consider diamonds like this. You can glue together along diamonds or along kind of segments along these boundaries of the Weil chamber, things like this, okay? And so this is known as so this real building, this is, so buildings were originally, I think, developed by Tietz in terms of what are known as discrete buildings, in terms of kind of p-adic arithmetic. And so the discreteness means that there's only, there's only kind of finite branching at each point. With the real building, that means there's going to be a continuum of branches at each point. So continuum is just kind of the cardinality of kind of the real numbers. And you can see, kind of, you can begin to see why the continuum hypothesis may kind of come into such a space like this. So it's still a, so this is still a metric space, right? This, call this kind of x infinity, d infinity, okay? All right. So, so let me try to explain a little bit why it has this sort of structure and why kind of the flats. So in particular, the kind of the flats survive, but kind of then, and then all the other information is kind of this complicated gluing data. So, and so let me kind of explain this in terms of some things that may be a little bit more familiar. So, so the asymptotic cone of Rn, so if you have kind of Rn tau inverse times the distance on Rn, this just goes to the standard Rn. Okay? So if you do this asymptotic cone construction as tau, so as tau goes to infinity, and I don't believe you need kind of any sort of fancy ultrafilter in this case as well. You kind of keep expanding and keep expanding and keep expanding, and it turns out that kind of the Gromov-Hausdorff limit, you're always looking at when you kind of get closer and closer, when you kind of expand out and expand out from kind of further and further away from kind of large perspectives, Rn still looks like Rn. And that's kind of a property of having, that has to do with kind of zero curvature here. Because if you take something with kind of negative curvature, this goes to an R tree. And so that's just a two-dimensional building. But this is kind of made perhaps a little bit more familiar. And so you can kind of think about this, for example. So this would be in H2, and you know there's kind of this standard picture of an ideal triangle, right? And so in particular, we know that geodesics, these are flats here. And so these are going to be preserved when we do the, so all the geodesics are going to somehow survive when we do this sort of limit. But if you kind of go from kind of, as kind of tau goes to infinity, we're going to have this sort of situation. Well, let me draw a better picture than that. I'll try to make it round. So I have these 3 points at infinity, but this is going to be very close to So this is going to be very close to, so the limit will be something like this. So the limit will be a little piece of a tree here. Okay? So with negative curvature, you get this behavior. With Euclidean flat curvature, you don't get any change. And so this space here has the structure, our x has R2 flats, it's rank 2, but kind of the normal space is an H3. So normal to each flat at each point, there's an H3 in our space. And so we get a combination of both of these behaviors. The flats are going to survive, and these things are going to kind of have this sort of behavior. And so what's going on here is we're going to have like a bunch of copies of R2. It respects the structure of the group. It's going to be this T, and then those are going to be gluing together with respect to the affine Weyl group. And I guess one thing to note is that in H2, you still have a group, right? But this is going to be, in one dimension, the Weyl chamber is just going to be positive numbers. And so when you glue two of these Weyl chambers together, according to this sort of recipe, that means you can get any sort of tree, right? Because, I mean, according to the affine Weyl group, you can glue along rays, you can glue, I think you can glue along points, you can glue along intervals. But when you kind of scale this up to the next dimension, you get kind of these more complicated pictures involving diamonds and kind of Weyl chambers and stuff. So it's just kind of the simplicity of the SL2R group and the maximal torus that gives us this sort of gluing, okay? All right, so that's a little bit of this. So let me kind of say so let me give you the theorem. And so the theorem is we're going to have this limiting minimal surface. It's going to land in this asymptotic cone. The asymptotic cone is quite nasty, but the minimal surface itself will be quite good. So and so again, kind of tau is cube root of t. So we're going to look at this m. Let's index it by tau. It's going to go from the universal cover of sigma. So this is, again, we have kind of the previous notation. This is the Riemann surface. This is the universal cover. Is going to go to x tau. And then kind of the omega limit is going to go to an m infinity, which is going to land in x infinity. And so kind of the image of m infinity is isometric to, again, on the universal cover, we're going to make a singular Riemannian metric out of the cubic differential. So this is kind of with the induced path metric on x infinity, but it's not totally geodesic. Okay? Okay. Is isometric to this. All right. So if you're used to kind of doing, I guess, dynamics on Riemann surfaces, you may have seen similar sorts of things with abelian or quadratic differentials. If you have an abelian differential, it's natural to kind of choose a metric of absolute value squared. If you have a quadratic differential, you just take the absolute value. So this is just the same sort of thing. We just need something because u transforms as dz squared to get this absolute value, dz cubed, to get this absolute value of dz squared, which you need for a Riemannian metric, you just take the absolute value 2/3 power. Okay? So if you've seen those sorts of things, this is not may not be so strange. So let me talk about the geometry of this metric. Okay. Okay. So this is going to be flat away from the zeros of U. So U is a non-trivial, it's not identically zero holomorphic cubic differential. It will have a certain number of zeros, but it's going to be flat otherwise. And the reason for this is rather simple, is that if you're not at a zero of a cubic differential, then you can choose conformal coordinates such that U is exactly dz cubed. Okay? All right. So, and then each zero, so at each zero of U, there's kind of a concentrated negative curvature. So like a delta function of curvature. And so there's kind of versions of Gauss-Bonnet that would work in this setting, for example. So, so we have kind of the following thing. So it's going to be, so this is going to be, so altogether we're going to have non-positive curvature in the sense of kind of NPC spaces. We're going to have geodesics. So geodesics are going to be straight. So geodesic is just kind of a path which is locally length minimizing. So if you fix the endpoints, this is, you cannot vary to get kind of so the geodesics are straight lines away from the zeros of U. So the notion of straight line just comes from the flat metric. And then at a zero, the Euclidean angle must be bigger than or equal to pi on both sides. Okay, so should say that. So what happens is with these concentrated negative curvatures, this has kind of a total angle at these is going to be bigger than 2 pi, is going to be, let's see, 2 pi plus k times 2 pi over 3. K is the order of the zero. Okay. So kind of the idea here is that with this concentrated negative curvature, it's a cone point, but kind of the cone has to be, in order to have negative curvature, has to be, angle has to be bigger than 2 pi. Okay? Smaller than 2 pi would be positive curvature. So you have kind of this sort of situation. So you have a geodesic coming in, it hits a zeros. They want to hit the zeros, by the way, in general. And then you have kind of another kind of coming out. And so you want kind of the Euclidean angle to be bigger than or equal to pi for both directions. Okay. And this is possible to have kind of this happen non-trivially because the total angle is more than 2 pi. Okay. So a consequence of this has let's see. So I call this 3. So we're going to have non-unique continuation of geodesic rays through zeros. So I mean, if you're kind of coming into this zero, then this condition, there's a whole interval worth of angles kind of going forward that satisfy this condition. It's just an inequality. So there's no unique continuation of rays. And this is the same sort of thing you will see in a real tree or a real building. So if you have like a geodesic in a real tree, that's just going to be essentially a linear path, right? But if you come to kind of a branching point, you can choose any of the branches, right? So, so you also get So on the universal cover, there exists a unique geodesic between any 2 points. Okay. All right. So that's kind of the geometry of this. So basically, this is Euclidean everywhere. When Euclidean, we're going to think about this limit here. In Euclidean, if things are Euclidean, at least on kind of a convex set, that's going to lie nicely in a single flat. And if you're at a zero, then it cannot lie in a single flat because you cannot kind of, the whole thing cannot accommodate this angle. So in this case, we're going to have to pass from flat to flat necessarily in order to kind of accommodate this total angle that's bigger than 2 pi. Okay? So that's how this works. So, so then there's kind of a question of how to embed. Okay, so there's a scheme for this. So let's choose a base point, say x naught in the universal curvature of sigma. And let's assume that it's not a zero. It doesn't really matter so much. And then what we have is we're going to look at kind of geodesic paths. From x naught. And so this is geodesics with respect to this flat metric. Okay? So in particular, we're going to have the following. So this may be our base point, and then we have kind of a number of zeros here. Okay? So C1, C2, C3. So each geodesic path will have kind of a number of zeros. I mean, there are some examples of Riemann surfaces where there are, say, geodesic loops that actually several geodesic loops which don't actually intersect any zeros. That's kind of an analog of something called Strabel differentials for quadratic differentials, and that, I've been assured, still happens for cubic differentials. But in general, for a general geodesic path and a general kind of Riemann surface and cubic differential, you expect this sort of thing to happen, right? Okay, so all right, so all right, so away from the zeros, u is dz cubed, so we're just going to choose some coordinate, and then z is equal to, so choose z. Z is r times e to the I theta. So this is going to be a, so now what we're going to do is we're going to let lambda 1, lambda 2, lambda 3 be real numbers, and we're going to order them like this, where these are given by the following. So this is going to be the L cosine theta, L cosine theta minus 2 pi over 3, L cosine theta minus 4 pi over 3. Okay? Where L is kind of the length of a path C, so one of these paths, for example, and theta is its angle, like this. Okay? So this is just, And so it's natural. So the thing is, when you're choosing a coordinate z, you can, of course, translate by z, and that kind of still does leave z cubed invariant. But more importantly, you can multiply z by a cube root of unity, and dz cubed will be invariant. And so that reflects the fact that theta is only defined up to multiples of 2 pi over 3. And so you must, if you consider theta, you must consider these other angles as well. Okay. That's just kind of the geometry of the cubic differential. And so we're going to have these three quantities. We're just going to put them in order like this. So then so now we're going to have a distance. This is due to Perot, and Perot, a vector value distance, which is going to be lambda 1, lambda 2, lambda 3. This is going to live in the closure of the positive Weyl chamber inside of the maximal torus. Okay? So then kind of the theorem is that the metric space distance in x infinity is given by kind of the sum of the angles of these paths, okay? So each one of these is gonna, if you kind of reorient this, this is going to be, this distance is going to be in the Weyl chamber, in the positive Weyl chamber. So I guess we draw that again. Okay. And so this is the metric, but kind of the path length. So the metric space, but the path length is the sum of is the sum of the distance, there's the sum of the lengths of the vectors, whereas this is the length of the sum of the vectors. And you can see that this is not totally geodesic by the fact that if you choose two vectors that are not parallel to each other in the closed positive Weyl chamber, like this, then the length of the sum of the vectors is not the same as the sum of the length of the vectors. So this is not totally geodesic. And the fact is, this is required because this essentially almost always happens when these geodesics hit zeros, which is the generic situation for geodesics. Okay? So there's that. Let's see, it's 10:28, so I have about 30 minutes left. Okay. So I guess now let me try to show. Yeah.
And so when these two segments will map to the same flat or different, typically there will be different flats.
They may be different flats. I mean, the thing is that there are lots and lots of flats. So you can there are kind of flats that are kind of natural from one point of view, but then there are, I mean, I think that it's a theorem of Perot that you have any two, you can find a new flat if you have any two kind of Weyl chambers meeting at a given point, as long as they're far enough away from each other.
Picture you drew in this positive Weyl chamber.
Yeah.
These two segments could be in different flats.
They're naturally in different flats, yeah. So the thing is, so in order for it to kind of remain a geodesic in the sense of this metric, we cannot kind of, so the thing is, once you hit the zero, you cannot just move away from it, right? I mean, that's going to make the path, so since these angles are both bigger than pi, if you move away from it, that's going to make the path longer. If you move away this way, it's longer. If you move away that way, it's longer. Okay.
So this orange triangle could be, there is some flat in which you draw that.
think so, but I'm not sure if that's the most useful way of thinking about it. Yeah, I think it's just because you can't kind of draw for a given ray or for a given geodesic. Yeah, no. So there's a theorem about real buildings that if you have a geodesic, then there is a flat that contains it. And I guess these are not quite geodesics. So, but yeah, I think that's still true, but it's not quite useful for what. There's not a geodesic that contains kind of a neighborhood of any of a point of the. There's not a flat that contains a neighborhood of any zero. But the rays you can do something else with, I think. Yeah.
Okay, maybe what was the sum of GI for you to know?
So these live in a vector space. So you can add them up. Like these two vectors live inside this vector space. They're in a cone, yeah.
Assuming they're in the same flat.
Yeah. So it's so yeah. The path doesn't naturally lie in kind of a single flat, although. I mean, there are lots and lots of flats. So I think it's I think there is a flat, but it's just you can't make it a geodesic. You can't kind of cut this corner off anywhere to kind of make it a geodesic. So let me try to show a. Let's see if I can get this to work. This meeting is being recorded, so let me try to share my screen. There's a. Okay, so I need the one of the screens is going to come down, I hope. What? Let's pray for it. No, I mean, I think it depends on somebody else doing something. Okay, thank you. Okay, no, both of them are coming down, it looks like. That's fine. Thanks. So it turns out that okay, so it turns out that there are specific sorts of not quite Riemann surfaces, but orbifolds where the cubic differentials are quite nice to deal with, and that is a triangle group. So a triangle group, you kind of take is specified by kind of the number of triangles. So this is a picture in hyperbolic plane and Poincare metric. And so it's specified by, this is a 3, 3, 4 triangle group. So 3, because there are 2 times 3, 6 triangles, or 3 black triangles at this vertex. And then there are 2 vertices where there are 4 black triangles here and here. So if you look at this as kind of the main triangle, then everything else is a reflection. And there are 3 here and 3 and 4 there. Okay? So it turns out that for the cubic differential here is exactly on this orbifold given by, so a fundamental domain for an oriented orbifold in this case would be given by a union of a black triangle and an adjacent white triangle, like this. Okay? And then they're going to be glued together. And they're going to be glued together in such a way that that it makes kind of naturally this Poincare disk, but we want to look at the metric given by the cubic differential. Okay? And so the rule for the cubic differential is that at a zero of order, so at a triangle intersection of order P, the order of the zero at this triangle intersection is P minus 3. So this one, this is a 3, 4, 4, so this is a 0th order 0, or not a 0 there. This is a 4, this is the 4 point for the triangle group. There's a 0 of order 1 there and a 0 of order 1 there. Okay? And then in this simple case, we can also explicitly describe exactly what happens when you pass to the this singular flat metric. So the singular flat metric given by the absolute value of u to the 2/3 forces all of these triangles. So I mean, away from the zeros, this is going to be in Euclidean space, right? So all of these triangles are going to be in Euclidean space locally instead of hyperbolic space, and they're all going to be equilateral. Okay? So you can imagine this. I mean, this looks, I mean, this is kind of in the center of our picture here. This looks like kind of already almost looks like, well, there are 7 equilateral triangles in this little patch of Euclidean space. But over here, if you have kind of the 0 of order 1, you're going to want to try to put, in a Euclidean way, 8 equilateral triangles together at one point. And so, of course, they won't fit in a single flat because there's this extra angle of 2 pi over 3 in this case. Okay? So, so you can see that if you kind of go all the way, if you take like a little loop around this 0, you cannot remain in a single flat. I mean, these geodesic paths are a little bit simpler in that respect, but if you take a little loop around this 0, 0 of order 1, or this 0 of order 1, you cannot remain in a single flat. And so you can see this is how this kind of, this picture has to fit inside of the, of this building of the asymptotic cone in a non-trivial way. You can't put everything in a single flat because it has to accommodate these angles that are bigger than 2 pi. So, so this gives kind of I don't know. This is kind of, and for me, this kind of gives a little bit more intuition about what's going on with this building and how kind of the various things kind of come together. Is that, of course, in a vial chamber, you also have kind of the angles are exactly going to be, the angle of each vial chamber is exactly going to be pi over 3, right? So that's what's kind of being reproduced here. Okay, so do you have any questions about this picture before the picture goes away? If the picture goes away? Okay, so let me stop sharing, and then I hope the did that happen? Okay, I think I successfully stopped sharing, but okay, and then these things are going up. Thank you very much for the help. Okay, so let's all right, so I have about 20 minutes. So maybe I can either say, I think I'll probably say, I can either say something about the proof or about kind of other geometric structures here. So let me say a little bit about the proof. I think that fits better with what's done already. And so that is, okay. All right, so let's, where was I? I don't remember where I was. I guess I'll just kind of I'll start over here. Doesn't matter, okay? Maybe I'll keep that statement up, okay? Okay. So I guess kind of the Hitchens equation, so these Hitchens system of equations, this kind of flat connection, simplify in this case for our value of phi. So I guess we're doing t times u here, 1, 0, 0. Okay. And so on sigma, I'll let kind of little sigma be a background metric. So hyperbolic. And then we have the simplification. They simplify to a single equation. Okay, and so with this last term, kappa of sigma is the Gauss curvature. So this would be, say, so this term would just be minus 2 times 1 for a hyperbolic metric. Okay, and then the Blaschke metric, the Blaschke metric ht is just this e to the mu t times sigma. Okay, Blaschke metric. Okay, so this is a semi-linear elliptic equation. One of the things that's nice about it is if you're used to these sorts of things is that as a function of mu, or mu sub t here, this whole right-hand side is an increasing. And so it turns out that when you have this sort of situation with kind of the Laplace operator over here, oops, no, there wasn't I forgot about that. So there's no e there, so it's just mu of t. When you have a Laplace operator over here, and this is increasing in the function value, then these are the good signs for the maximum principle. And so you get, so on sigma, so at least when sigma is compact, but also in lots of non-compact settings as well, there exists a unique mu of t as a solution. Okay? Okay. All right. And so so you get kind of from sigma and u, or t times u, you get, in addition, in a unique way, this h of t, which is the e to the mu t times the background metric. Okay? And so if you have seen, you may have seen some equations like this before. I mean, in Mike Wolf's thesis, when he's studying quadratic differentials, and with kind of slightly different constants like this and this, if this were a quadratic differential, this is kind of Wolf's equation for harmonic maps between hyperbolic surfaces. And again, that's a reduction of Hitchin's system in the case that we talked about yesterday. Okay, so all right. Okay, so let's keep this picture up. That's going to be useful. So I guess let me say kind of like Ci is like, there's an Li e to the square root of minus 1 times theta I. So these are the L's and the thetas. Those are going to come up. Okay. All right. So there's a kind of a theorem in this case. So that I do kind of a version of this which is not very precise, but it's quite general. There's a version with Collier and Lee and Mochizuki that kind of the holonomy, so this is of the flat connection nabla along the Ci, is approximately the exponential of, let's call this tau times lambda 1 to the I, tau times lambda 2 I, tau times lambda 3 I, plus an error, okay? And so the error in this case is at least when you kind of stay away from the walls of the Weil chamber, and possibly otherwise, although I haven't tracked down the details. This error, at least in Mochizuki's formulation, is very, very good. So these are kind of exponentially growing things. This is like something like e to the minus e to the tau. Very good in Mochizuki's, but I'm not kind of quite certain about kind of the boundary of the Weil chamber, although I think it may work in that case as well. But kind of this one is completely general. It's just the estimate. The error isn't very good. So in this case, but at least kind of the error here is going to be smaller than the largest term. So you remember lambda 1 is the big one. This is the next one. This is the smallest one. Okay. So the error is going to be less than e to the t, or e to the tau lambda I. Okay. All right. So near the zeros, we're going to rescale u to the so tau, Tu to be of the form z to the m dz cubed on the complex plane. Okay? So there's a rescaling of this, which is not quite the same as tau. It's some other power. I think it's t to the 1 over m plus 3 or something like that, but it still works. And we're going to get, this is going to be a picture of a regular convex polygon. So this is due to Dumas and Wolf. Okay? And so then there are also going to be, so for this we have kind of the, along here we have kind of the holonomy of C2. There's also going to be a, let's see. Let's trying to figure out which way I'm numbering these. So this one I think is going to be a 2. This is going to be a UI. So there's going to be a component here. We're going to multiply these holonomies together, but this is going to be a, and so then this UI is equal to a product of unipotents, so determined by the geometry of the polygon. So Dumas and Wolf's polygon plus some errors. And again, kind of, and the error estimate in this case, this is due to us, and the error estimates here don't seem to be that great. But, and so then the holonomy is going to be, say, the product of the holonomy of Ci inverse times Ui times the holonomy of Ci minus 1 inverse. So the U, this is just kind of some notation, the fact that I'm putting the inverse in here. Okay? And so what happens here is that the error terms, at least here, are not very good. And so what we can do is we can show that the terms in the UI matching the largest terms in the holonomy of the Ci and inverse and the holonomy of Ci minus 1 are positive. Okay? And so this is kind of a detailed reflection on what Dumas and Wolf did. We have to kind of write down a bunch of cases. So in particular from this, we can kind of show, we can pick out the largest eigenvalue of the holonomy and kind of the, and it turns out to be the same as the singular value, which is, I guess, a little bit more relevant to us as the sum of the so the product of exponential of tau lambda 1 I. Okay? So lambda 1 in our formulation, this is the largest one. And then the lambda 1, this is going to be our, so you remember this is going to be the L times cosine theta. Whichever, choose whichever one of those is larger, okay? And so kind of the main technical, one of the main technical points is to ensure this little bit of positivity, because in the case where your path may be, your geodesic segment may be at the boundary of a Weil chamber, then there's not just one largest. There may be two largest ones. And the thing is, you want to make sure that when it matches up to the next one in some complicated way, you may have kind of two largest terms as you're kind of multiplying these matrices together. You want to make sure that they don't cancel out later. So you want these coefficients to be positive. So these things are positive, at least up to some error. The relevant coefficients here are positive. These things are positive. Okay? And so that is this. Okay. All right.
by the geometry of the polygon is it's a regular.
It's a regular polygon. We actually, Dumas will kind of treat the case of other polynomial cubic differentials, in which case the polygon will not be regular. We actually, for this lemma, we showed this for general polygons, which at least theoretically should correspond to, so we're looking at rays of cubic differentials. You could also kind of move around in the moduli space and look at some other path. And so in that case, some of these limits should correspond to regular polygons, to non-regular polygons, which, I mean, we checked this part, but there are various other things which didn't get checked yet, so.
For a regular polygon, these unipotents
They are, yeah. So the thing is that the unipotents are the following. So if you have a polygon, if you look at kind of, you have kind of inscribed triangles and circumscribed triangles, because you're in kind of RP2, you can kind of take these out. And so if you go from an inscribed triangle and kind of move from one inscribed triangle to the next circumscribed, there's a unipotent. And so this is determined by just where the vertices lie. And the positivity of the relevant term is guaranteed by the convexity of the polygon. It doesn't need to be regular, it just needs to be convex. So if it were not convex, then you would get negative terms, you just wouldn't get anything. So. Thanks. Okay. So the thing is, you can kind of find the largest term. And this largest term is enough to compute the largest, asymptotically, the largest singular value and eigenvalue of this holonomy. And so, okay, so you get kind of the logarithm of the holonomy has the largest term as kind of tau, so lambda I1 plus little o of tau, okay? So that's what we get. So we don't get kind of, if we had kind of Mochizuki style errors for everything, then we would get much better than this, but we don't, at least not yet. And so, but then we're going to use kind of this. So our formulation was that we needed not just kind of this is going to be the eigenvalue, so the largest eigenvalue or singular value. So the thing is that you remember kind of the distance in the symmetric space that needed all of the eigenvalues, not just the biggest one. But there's a trick in SL3R to get all of them. And that is, in SL3R, we can consider the path in reverse to get the largest of Hall inverse and so that would be the smallest of log Hall as tau plus lambda 3i, tau times plus little o of tau. But now, lambda 2i is lambda 1i, or minus lambda 1i minus lambda 3i. So you get all of them. So, so this is kind of special to SL3R only. So this doesn't work, say, in SP4R, which is kind of another, the next most complicated rank 2 one. So, for example. Okay. All right. And so you kind of, I guess, you rescale the distance which is by tau to the minus 1, we're going to take some omega limit. We're going to get the distance in x infinity. Okay, so this applies for any geodesic path we have this distance. And I guess another thing in kind of checking this this lemma about kind of the terms in the unipotence, this critically uses as well that we actually have a geodesic passing through the zeros. So you need the fact that it's at angle at least pi both ways, because you will get zeros, for example, if you try to kind of do a non-geodesic path, whereas kind of this, if this is like a right angle from this direction, then that's not minimizing. So that's that. Okay, I think that's it. Thanks.
Any questions?
It's okay, I can just speak loud. Yeah, so you mentioned about that Gauss-Bonnet theorem for in the limit negatively concentrated regions. So can you elaborate a little bit on that? Especially in the light of the picture where you showed vertices where angle adds up to more than 2 pi, then you have to change the flats.
Yeah. So the thing is that if you try to do the Gauss-Bonnet theorem, then kind of the computation, so there are various Gauss-Bonnet theorems. So the thing is you can assign various negative delta functions of curvature to these things, and then via kind of this defect of the cone angle. I don't remember what the formula is, but if you add them all up, that's the only curvature on the surface, you get kind of the formula from Gauss-Bonnet. You may need to do something a little bit different if you want to do kind of geodesic triangles or something like that, especially if one of the points kind of lands on the zero. Yeah, but you have this version of Gauss-Bonnet, at least for kind of closed surfaces. And I'm not sure in general, this is one of the things that I'm not sure, I haven't really asked people about it, but maybe I'll ask you guys what is kind of a general setting for Gauss-Bonnet? How singular can these things be? Because there are, if you have a surface that has an NP, so let's say kind of simply connected surface that has a complete non-positive curvature metric, then you may be able to take quotients, for example, to get something closed. It's kind of a question of like, non-positive curvature metrics can be quite singular, right? So it doesn't have to be, so this is kind of Riemannian almost everywhere, right? Of course, if negative or non-positive Gauss curvature at those points, but there are lots and lots of these things that could be kind of much more singular. It doesn't have to be Riemannian, it could be like a Fensler metric, it could be worse than that, it could be all sorts of things. But so I don't know, but that's something I'm kind of interested in, but I don't know kind of what the answer is or how generally you can kind of apply Gauss-Bonnet. But I know you can do it here. Thanks.
Make sure that I understood what you explained correctly. So if you, I guess you had total angle 2 pi plus k times
2 pi over
2
3.
pi by 3,
Yeah.
where k is the order of the zero. First of all, these zeros could have different orders, and if the total angle exceeds, let's say, more than multiple of 2 pi, then you enter different flats.
Yeah. So you have to have, so the thing is, if you're going to put, so we have kind of this path, at least, so kind of locally, kind of the paths are conform to the length here. So if you have this sort of embedding into the building, then on each, say, convex subset of Rn, where you have to kind of exclude the zeros, you have to avoid all the zeros, then you get that it's just a standard Euclidean metric. And then the zeros you have to kind of handle by this sort of, each of these little loops, you have kind of more of this monodromy. And so you have to kind of pass to a different flat every time you take a loop around a zero.
Eventually, you could go to many copies of flats, go through many copies of flats. Can that happen?
Yeah, I think you can, so in this situation, I believe that if you start developing this situation for like this sigma tilde, then certainly you only need, say, a countable number of flats, right? They're kind of a countable number of kind of fundamental domains in the universal cover, right? Because they all have some area. So yeah, so I mean, I guess it depends on, I'm not sure how few you can kind of whittle it down to, but I mean, I think in general, you probably need a countable number for all of them. So unless you're just looking at a neighborhood of a geodesic or something quite simple. So thanks.
I have a question which is slightly off.
Okay.
So instead of q equals to 0, if you do q is equal to a non-zero constant.
Well, q has to be a quadratic differential. So the q is like, so yeah, so q is, yeah, but it has to kind of be holomorphic on the Riemann surface, right? So if you have, say, so there's not like a notion of constant. So yeah, so like q is equal to kind of some q, I'm just kind of abusing the notation, q times dz squared locally. So even if kind of, if you choose this coefficient to be constant, then that depends on your choice of local coordinate. So if you change coordinates, then it's not, and in fact, there are no, if you want to find kind of a section of this sort of bundle to be constant, to choose as constant, then it would have to be non-vanishing, right? And so any holomorphic section of this bundle, k squared, over a higher genus Riemann surface has a certain number of zeros by Riemann rock. You can, more than there's a certain positive number.
Corresponding of CMC surfaces, the minimal surfaces, can you relate it to Higgs bundle?
Can I? Oh yeah, so the answer, yeah, I can answer that. The answer is no, because I haven't thought about it, but I'm not sure. Can one do this? Perhaps, yeah. Yeah, so I don't know I don't know what people have thought about, so in this situation, so it's a good question, thanks.
Any other questions? Okay, so we thank everyone.
Okay, thanks.